Okay, so we've done a lot with the Riemann integral, and one thing we know about the Riemann integral is if we're going to integrate something using that technique, it needs to be a bounded function. You also know or suspect from your earlier calculus classes and physics classes that sometimes there are unbounded functions that we nevertheless integrate. So we need to have a way, again, of making sense of that, making it precise. What does it mean to take an unbounded function and somehow find the area under the curve in a rigorous way? So this is the improper integral. Okay, so here's a quick example. You take a function like this, say 1 over root x from 0 to 1, and maybe plug the hole with something. All right, so this guy he's defined on the closed interval from 0 to 1, but it's unbounded, right? So this is not Riemann integrable. But we expect that we can integrate this thing. So our expectation is, just from what we've seen in calculus earlier, that if we integrate this thing, right, we should get a 2 root x from 0 to 1, which is 2. And that's perfectly finite and perfectly well behaved. So we want to make sense of this rigorously. So in order to do this, we need to somehow exclude the tricky or the nasty regions and try to use what we know about limits to see what happens as we come close to including the tricky regions without ever letting them actually belong. So to do this, we're going to use the concept of local integrability. So we're going to say that f is locally integrable on some interval, which could be a closed interval, it could be open, it could be half open, half closed. It could include infinity or minus infinity as some of its endpoints, so I'm being very general in what I mean by this. If it is integrable, by integrable I mean Riemann integrable, that we can do these upper sums and lower sums and they get close to each other, arbitrarily close to each other, on every possible finite closed subinterval. Yes?
Strict subinterval?
Just has to be finite and closed. Now, if you happen to be starting with an open interval and you want something that's a subinterval of that's closed, it will be a strict subinterval. But yeah, that's a great question. So here, I'll do actually an example right here. If we take this guy here, 1 over root x, okay, so this is not going to be locally integrable on the closed interval from 0 to 1 because it's not Riemann integrable from 0 to 1. But we're going to be able to say this is locally integrable on the interval from 0 to 1 if I exclude 0, right? So you choose any closed subinterval of this. It will necessarily not include 0 in it. And then you're fine. Then you've got a perfectly nice continuous bounded function. And you can integrate it, right? We can include 1. We cannot include 1. It doesn't matter. That doesn't cause problems. As long as we're excluding 0, which we have to do for this definition, we're in business. Okay, again, we can also do this on unbounded intervals. So I could say that x squared is locally integrable on the entire real line. Okay, of course, I can't integrate this thing from minus infinity to infinity, right? That's going to blow up on me. But if I take any closed finite interval that I like, I could go from minus 10,000 to 8 or whatever, I can do this integral, and I'll get a number, a finite number. So this is locally integrable on this unbounded interval. Okay, so we have the concept of local integrability. Then we can use this to define our improper integrals. So we're going to say, let's say that f is defined and locally integrable on, I'm going to take a half open, half closed interval here. So a to b, where we exclude a. And you can write the same kind of definition the other way around, keeping a and excluding b. But this is actually important. It's half open, half closed. Okay? Then we're going to define the improper integral of f on this same interval by okay, and now what we're going to do is say, well, as long as I move in a little bit, exclude a, I have an integral that I can definitely do, because this is locally integrable. So what I'm going to do is try to move in a little bit, not a, but something a little bit bigger than a, integrate from c to b. And then what I need to try to do is take the limit. Let c get arbitrarily close to a. I can't do this from both directions, right? I don't want c to ever be allowed to be less than a. So we're always going to be coming at a from above and descending down on a. And that means if we're coming at a from above, again, we're doing an integral from c to b, c bigger than a. This integral is going to be perfectly well defined because this function is locally integrable. So we're going to call this the integral of this. And this is how we define it if this limit exists. Okay, and again, this is allowed to include a as minus infinity. That fits within this definition just fine. B has to be some number here. Okay, and I will just say a couple things. If the limit is plus or minus infinity, we're going to say that the integral diverges. That's one comment. And secondly, there's nothing really special about the fact that I decided to do open on this side and closed on this side. I could have obviously done it the other way around, and then we just have to make sure we're approaching b from below. So we can similarly define improper integrals on a to b, where we include a and exclude b. Is a reasonable definition? Happy with that? Okay, good. Okay, so the next question is, what about a function that is locally integrable on a completely open interval? But potentially with problems at both ends of this interval, right? So we may have f blowing up at a and blowing up at b, or maybe a and b are minus infinity and plus infinity, or things like that. How can we define this integral? Yeah.
We can split it at a well-defined point.
We have to split it at a well-defined point. So that's what's key. It's not going to be enough to say, let's just do one limit where we let this guy go to minus infinity and this guy go to plus infinity. We really are going to have to split this into two half-open intervals. Okay, so let me try to convince you why. Let's take something like this. So the naive approach might be to say, well, this is going to minus infinity, this is going to plus infinity. Let's just try doing this integral, say from minus r to r of sine x dx, and we let these limits go off to infinity. What's the integral of sine function from minus r to r? Zero. Sine is an odd function, right? Right? So whatever area we get on one side, we're going to get negative of that on the other side. So this is straight away 0. So that's one way to get an answer. But if we do approach number 2, we should expect that we could equally well break this up into, say, minus infinity to 0 plus 0 to infinity. And what's this integral equal to? It doesn't exist. It's undefined, right? You do an antiderivative of this, and you get a cosine, a minus cosine. And you try to take the limit as x goes to minus infinity, and it's just going to keep oscillating for ever and ever, right? We're not going to get a well-defined limit. And this doesn't exist, right? So these are two approaches. They give very different answers, and they can't both be right. So again, we need a precise way to define this thing so that when we get an integral like this, we know what's the right way to define it so that we only get one answer. We should only get one answer. And what's going to be reasonable is to say, as we've done many times, let's put this in terms of something that we already have precise definitions for. Okay? Doing something like this, it's not so precise because I could have done minus 2r to r, for example. And that would still let these limits go to plus or minus infinity. There's lots of ways of doing that. This is a little more precise because now we have a precise definition of this, right? This would be half open, half closed interval, including 0, excluding infinity. We know how to write down a precise definition of this. We know how to write down a precise definition of this. So this is really the answer that we want to be getting out. It doesn't make sense to take an oscillatory function and integrate it all the way up to infinity and expect it to converge to some value. Okay, so we're going to say if f is locally integrable on the open interval, okay, we're going to define the improper integral here. Okay, so of f on this interval, by, so again, we're trying to integrate from a to b. And we split this up. So we pick a point in the middle. So we go from a to c, f of x dx. And now we have a way of deciding if this thing exists and what its value is, because c is a perfectly well-behaved thing in the middle, right? This is locally integrable in here, so c is valid. And then we keep going from c to b. And again, this is perfectly well-behaved. And what are the conditions? We need to make sure c lives strictly in the middle of these things. So he's away from the problem regions. And we're going to be happy with this definition as long as now both of these component integrals exist. So if both of the component integrals are convergent. Okay, and again, I'm harping on this. You need to split it up in this case. And on the exams, people will always look at this, and in the panic of the moment, will forget to split it up and get wrong results. Right? We need half-open, half-closed intervals. Each integral can only have one problematic thing to deal with at a time. We can't deal with multiple problematic things at one time. Okay, so for example, this would be a reasonable way of evaluating an integral. Okay, so we look at this and say, well, infinity is not a number. We can't do Riemann integrals, Riemann sums on an unbounded interval. So this is a problem point. 0 is a problem point because we're going to end up with this function not being defined there. If we exclude those points, though, in the middle, we've got a perfectly nice continuous function. So this is certainly locally integrable. So we know this, at least. Is certainly locally integrable because it's continuous, and continuous functions are integrable. Okay, so we're in business to try to split this thing up, at least. Whether that result will converge or not, we don't know ahead of time, but we know that we're at least in a place where we can hope for this thing to be integrable. Okay, so we need to split it up. Again, we have 2 problem points, so we need to split this up. So we're going to choose any value of c that's positive, anything that's between 0 and infinity. 1 would work. Yeah, I'm not even going to specify what it is. I'm just going to let it be c. But you can specify. It's fine. Okay, so we're going to do our 2 integrals. First of all, we're going to say we need to do the integral from 0 to c of this function. Okay, this is still an improper integral, right? Because 0 is a problem point, but c is fine. So we know we need to write this as the limit as a goes to 0 from above, the integral from a to c. Right? So this is how we always rigorously deal with improper integrals. We write them as limits. And then I'm just going to notice that this function happens to be a total derivative. So this is something that we can actually integrate exactly because we know the fundamental theorem of calculus. Right, so this guy is going to be the limit. A goes to 0 from above. And we get, okay, e to the minus 1 over x is our antiderivative. So we're going to get e to the minus 1 over c minus e to the minus 1 over a. Okay, a goes to 0 from above. Again, it's actually going to be important here that this is just a one-sided limit. As a goes to 0 from above, this guy is going off to minus infinity here in the exponent. So that term will go away. And we get e to the minus 1 over c. Okay, same deal for our second part. So our second part, we're going to keep going from c to infinity. This time, we need to exclude this problem point. So limit as b goes to infinity of the same function okay, we've got the same antiderivative as before. So e to the minus 1 over b minus e to the minus 1 over c. Okay, so now this time this exponent is going to 0. So we're going to get 1 minus e to the minus 1 over c. Okay, so we split this up. Both of the component integrals exist. We can come up with values from them. And that means we're in business. So that's going to mean then that the integral from 0 to infinity of this thing is just the sum of these two things. And very happily, right, although I didn't pick anything particular for c, it's going to fall out, and we just get 1. Again, you don't have to leave general c here. You could pick c equals 1 or c equals 10 or whatever you like. I left it in there just to illustrate and make clear that this actually does fall out. It doesn't matter which intermediate point you pick, and that's important if we're going to get a well-defined value. Okay, so we have a definition of these things. Now let's try to learn a little bit more about some of the properties of these, or how we can look at a function and decide, yes, this improper integral is going to exist, or no, it's not. Right? And knowing that in the real world, most of the functions that we encounter are not going to be this simple where we can just look at them and write down the antiderivative. Yeah?
So in the case where we are trying to evaluate something like
Yeah.
that, if f is continuously integrable at c, the midpoint will always cancel out, right?
The midpoint will always cancel out.
So could you just skip to a double integral on a and b?
How do you mean a double integral in a and b?
Like limit as a goes to something, comma limit as b goes to something, where the order doesn't matter.
Where the order doesn't matter. So yes, you should be able to do a and b as it's not a double integral, it's a double limit.
That's right.
I want to be careful when I say that. We haven't actually defined double limits,
Okay.
right? So you want to be a little bit delicate there. So this strategy at least puts this in things of terms that we've rigorously defined and we know they exist and what they mean. Any other questions before I move on? Okay, so this stuff so far should not look too foreign, I hope, right? You've seen improper integrals before. You haven't seen them defined quite this precisely maybe, but you've done them. So let's just try to get a little bit more abstract now and say that, again, most of the functions we see are not like the functions we see in Calculus 1 where we can just write down the antiderivatives. So what are the easiest functions to deal with? The easiest functions to deal with are usually the ones that don't change sign. So I'm going to say the easiest functions to deal with are non-negative functions. Okay, so this is one result. If f is non-negative and locally integrable, on some interval, then we can write down a condition that decides whether this thing actually has an improper integral that converges. So we're going to say this is the condition under which this guy exists. If the following function so capital F of x, I'm going to define as the integral from a to x of f, if this is bounded. Okay. But first of all, I'm going to emphasize it matters that f is non-negative here. So we did an example before of the sine function, right? If I try to integrate sine from, say, 0 to infinity, and I say, let's instead look at something like this, 0 to x of sine of x, that's always going to be bounded, right? There's a maximum amount of error you get before you start canceling it out again. So this guy is going to be bounded, but we know that the integral doesn't converge. So it is really, really going to be important here for f to be non-negative if we're going to pull this theorem off. Yeah.
For f of x, capital F of x to be bounded, it's only on AB.
On AB, exactly. Wrong way. So it means that, okay, I exclude the trouble point, right? I integrate from a to wherever I like as long as I don't hit the trouble point. And I might get different values. We don't know what will happen, but there's some bound that this thing can never exceed. Right? And again, if I have an oscillatory function that becomes negative, positive, this theorem is definitely not going to work. So for the sine function would fit all these other conditions, and we know it's not integrable from 0 to infinity. Yeah. If both A and B are problem points, then you would still be able to do this, yes. Right? And you could do it rigorously exactly the way we just did, by splitting it up and apply this theorem twice. Apply this from A to C and then apply it from C to B. Hey, so here is why this works. Okay, so we know that f is always bigger than or equal to 0. That's important. And now I'm going to say what happens if x is bigger than y. And capital F of x, we know, is equal to the integral from 0 to x. Okay, this is, I'm going to split this up, the integral from 0 to y plus the integral from y to x. These are both perfectly well-defined things. Okay, and this is my capital F of y, right? Integrating from 0 to y. That's how I define this thing, integrating from my lower limit to whatever the argument of this is. So this is my capital F of y. This, if I use my mean value theorem for integrals, this is going to be equal to f of c times x minus y for some c between x and y. And we know that this term is non-negative because we said f is always positive or 0. It's never negative. And we started by saying x is bigger than y. So this is positive. What does that mean? That means capital F of x is always bigger than or equal to capital F of y. All right? So if x is bigger than y, fx is bigger than f of y. Right? This is a monotone increasing function, in other words. And that we should expect, right? We have a positive function. I'm saying as I increase x here, so I increase the amount of its area that I want to include, the value should go up because it's all being counted as positive area. So this is reasonable. I think this is fairly intuitive. So f is monotonically non-decreasing. Okay, so then if I look at the thing that I'm actually trying to compute, the thing I'm actually trying to compute is the integral from a to b. I probably should have a as my lower limit here. So if we go back to the integral that we're trying to compute, the integral we're trying to compute is the integral from a to b. So the integral from a to b of f of x dx, let's call it f of t dt. We said that b is the problem point. So this is going to be the limit as x goes to b from above of a to the x, f of t dt. What's that?
Should we be approaching b from below?
We should be approaching b from below, thanks. Okay, so this is this limit. This is the limit as x approaches b from below of nothing but capital F of x. And does this limit exist? Why does it exist? It exists because it's monotonically non-decreasing, and that means if I'm taking a limit out to toward the right endpoint of this thing, what I'm actually going to pick up is the supremum of f of x on this interval. Right? We know the supremum is well defined. The supremum is always well defined, and we know it's finite because our theorem said capital F is bounded, right? If capital F is bounded, it has a supremum. And that means we can get arbitrarily close to the value of the supremum. The only way we can do this for an increasing function is by getting as far to the right as we possibly can. So this is nothing but the supremum, which exists and is finite. Since we were told that capital F is bounded. Okay, this is since F is non-decreasing. Okay, and that's the result. Okay, so if you happen to have a positive function, there are some tricks for how we decide if this thing is integrable. Right, so it may be a positive function but difficult to work with, but if we can put some bounds on this function, we might be able to look at this capital F and say, well, little f is bounded by something that's easier to work with, and we can maybe prove that this is bounded, and that means we know actually little f we can integrate, and that means, okay, it's fair game. It's something to put in a model of some physical system. It's fair game to start trying to do some numerical calculations here and not worry that we're trying to compute something that's actually infinite or oscillatory and that our numerics are going to give us meaningless results. Okay, but again, that only works for non-negative functions or non-positive functions, this particular theorem. Okay, I guess one example where we might use this is, say, if we wanted to do the integral from 1 to infinity of, say, absolute value of sine of x divided by x squared, for example. Right, then we'd say, well, sine of x over x squared is certainly non-negative. It's continuous. That means it's locally integrable. Okay, and if we were to look at this capital F of x and define it to be the integral from 1 to x of sine x over x squared, let's not reuse x in so many places. That's not such an easy integral to do exactly, right? But I could say we have comparison results that say, well, this is less than the integral of 1 over t squared, for example. Right? This is, we know how to integrate from 1 to x. Okay, so this is going to be 1 minus 1 over x. Okay, so again, I don't know exactly what capital F is, but I've got some bounds on it, and I can say for x going between 1 and infinity, this thing is bounded, right? So for x belonging to 1 to infinity, capital F of x is always going to be less than or equal to 1. Right? That means capital F is bounded. I mean, it might be a lot less than that because, again, this function is not 1. This function does something. It bounces back and forth between 0 and 1. We don't know exactly what it does. So capital F of x is less than or equal to 1 and is bounded. Right? And then we're in business. So I have a function. I can't integrate it exactly. I build this capital F. I can't evaluate it exactly either. But I could put some estimates on it and say this is bounded. This function, because it's positive, is well behaved. So I can therefore say that means that actually sine x over x squared, this integral from 1 to infinity, converges. It's well defined. Right? And again, it's ugly, and I might not want to try to do this analytically by hand, but if this pops up in a model of some physical system I'm working with, I'm not going to panic that this is going to give me infinities. If I need to evaluate this, take out some code that we have for doing numerical integrals, and I'll be happy that it's going to give me reasonable results. Questions on that example? All right, so then we can also have comparison results. I did something like a comparison result right here, actually, right? I did not apply the comparison result for improper integrals. From 1 to x, this is a perfectly well-behaved Riemann integrable.
All you need is an upper bound on it because it's, we know that it's positive.
I only needed an upper bound because I know it was going to be positive. That's right.
This theorem works for...
It would also work for negative functions, yeah. That's right.
Okay.
Yeah. So here, I mean, I can get a lower bound here too and just say that this is the case.
Right. That's
Yeah.
fine. That's about.
But yeah, it was the upper bound that I was really worried about here because I happen to have an increasing function. Right. That's right, because we knew that the problem point was going to come over here at the right end point, and this thing is going to get bigger and either get bigger and approach something finite or get bigger and blow up on us. Okay, we have a comparison principle, a comparison theorem rather, for looking at these improper integrals. So let's say I have two functions. If f and g are locally integrable on some interval, whatever it is, and they happen to be ordered, so one function is always sitting above the other function, then okay, and now what I'm trying to do here is not necessarily get a handle on the values of these integrals. What I'm trying to do is say, do these actually converge or do they diverge? Do these integrals make sense or do they not make sense? So there's two parts to this. One is that if I take my bigger function, maybe my bigger function happens to be have a simpler form, and I happen to know this converges, then my smaller function is also going to converge when I integrate. This again applies to positive functions, right? We're not looking at cases of like a sine function, which will stay bounded maybe by nice things, but potentially just oscillate on us. And secondly, if my smaller function diverges on me, then my bigger function is also going to diverge on me. A lot of this is very analogous to what you learned about series, and we're going to be covering series in Chapter 4, and many of the techniques are similar. This may be not surprising because integrals we've actually defined using some kind of series, right? So certainly adding things up and integrating things are intimately connected, and there are actually a lot of similarities in the techniques we use. I'm not going to prove this here. It's simple proof, and it uses the same kind of techniques that we just did, relying on the fact, again, that these guys are positive, and that means capital F and capital G are these increasing functions, and we can bound them in terms of each other using other comparison results that we have just for the standard Riemann integral. Okay, but let's do an example. Maybe this is my function, 0 to 1 of 2 plus sine of pi x divided by 1 minus x to the pth power. And in the interest of never having to write all that again, I'm going to call this I. And we want to know, does this converge or does this diverge? And I don't know about you, but I don't particularly want to try to evaluate this thing analytically to decide. We know there's a problem point at x equals 1 potentially. So let's try to compare this to something that's a little easier to work with. And the good news is when we have these trig functions popping up, comparison results are usually easy to come by because we know these sine and cosine functions stay between -1 and 1, right? So we know that, secondly, we know this is always going to be positive, right? That's important too. So this is going to be, what's the smallest it could be? The smallest it's going to be is when this thing hits -1. So that's 1 over 1 minus x to the p. It's less than or equal to my function. And the biggest it's going to be is when this hits +1. So that's 3 over 1 minus x to the p. Okay, and now there are different things that are going to happen depending on how big p is. Okay, so if we do this integral from 0 to 1, this is going to converge if p is less than 1. Right? And it's going to diverge if p is bigger than or equal to 1. Right? And you just need your standard calculus rules that you know to evaluate this thing and work that out. Using an improper integral, because again, this guy is a problem point. Okay? And that means if we multiply it by 3, that doesn't change anything, right? So what do we know? We know that for p less than 1, or in the convergence case, we have that this integral converges. And that means if I integrate my smaller function, which is still positive, it's also going to be a convergent integral. So that means that I converges. This more complicated integral is fair game for us. On the other hand, if p is bigger than or equal to 1, then what happens? Then we integrate our smaller function, and it diverges. And if this smaller function is already getting out of control, going up to infinity on us, the bigger function is going to do the same thing. And that means, in this case, I diverges, and we shouldn't try to integrate it. Right. This was a particularly simple case because in some sense f is bounded by the same function in both directions. So it's really going to behave exactly like this function behaves. Of course, in more complicated cases, you might have a different function here and a different function here. Again, you need to make sure you're looking at the correct one when you're doing this analysis. Because if the smaller function converges, it doesn't tell you anything about what the bigger one is going to do. If the bigger function diverges, it doesn't tell you anything about what's going to happen over here with the smaller one. So you need to get the order right. Yeah.
I want to switch the cases.
You want to switch the cases.
Like it seems like it would diverge when p is less than 1 and converge when it's greater.
P is less than 1. For example, p equals minus 2.
Yeah.
I get actually 1 minus x squared.
Okay.
Right?
Yeah.
And that's perfectly well behaved.
Okay.
Things are going to get worse as p gets bigger.
Yes. Okay. Cool. Yeah.
You're welcome to go evaluate this thing by hand.
Let's try it out.
And okay, you're thinking about your p-series and things like that. In that case, the problem isn't down here. The problem is that you're going off to infinity. So it's a different singularity that's happening. Yeah. Yeah. Yeah, the singularity is a different point. If I had said, let's integrate from 2 to infinity, then that would have been a different ballgame. Okay, so positive functions are nice. And that means we want to use them whenever we can, even if we don't actually have positive functions to start with. So this is another set of techniques we can work with, is to say, let's talk about absolute integrability. Okay, so I'm going to say that a function is absolutely integrable on some interval. on a to b if, okay, again, we should always start by having a function that's locally integrable. So f is locally integrable on this interval. And we can integrate its absolute value. Now, the nice thing about asking about absolute integrability as opposed to just integrability is now we're in the case where we're working with a function that is non-negative, right? And we can use our tricks and tools that we know for non-negative functions. We have these comparison tools that we have. We can look at this antiderivative function, capital F, and ask if it's bounded. These kind of things all work, which they didn't work for little f. Yeah.
For proper integrals, we had the result that that bounds the absolute value of the integral. Does that still hold for these?
That will still hold for these, yeah. And you can, again, you can do this. You're taking limits of a bunch of proper integrals, right? So you get bounds on each of those.
Okay.
Okay, so you're already hinting at the fact that this should tell us something about the integral of f. And indeed, this is a theorem. If f is absolutely integrable, on this interval, then we can do this, and it works. Okay, I can't just straight off use my comparison results that I had here, because the comparison results that I had for improper integrals require f to be, these things to be positive or to be non-negative functions, right? So they're not fair game here. What I can do is try to use a trick. I need to bring in the absolute value function. Okay, I haven't changed anything here. I've written it in a funny way, but I have not changed anything. Now, what I really want to be able to do is break this up into two pieces, into this piece with these two functions and this piece. So let's see what we can notice. First of all, we know that this guy converges. Secondly, if I look at this function, what are some bounds I can put on this function? It's non-negative, yeah. And what's the biggest it could ever be? 2f. 2 times the absolute value of f, exactly. Right? Because we know this function is at most the absolute value of f. And similarly, negative of this function is at most going to be the absolute value of f. Right? And it's always going to be less than the absolute value of f. So we've got bounds on this function. So this guy, right, f on its own, I can't use my comparison result because because he's allowed to oscillate from positive to negative. This guy is always not strictly positive, but he's always non-negative. And I have another function to compare him to. So I'm in business with comparison. So since this guy converges, right? We're given f is absolutely convergent. That means if we multiply it by a constant, it's still absolutely convergent. That means that this guy converges as well. Now my comparison result is valid. Do we agree with this? These pieces are both fair game. So if I put them all together, we can say that if the component integrals converge below, then the thing that I want, a to b f of x dx, is equal to the integral from a to b. I'm just going to pull out a minus sign. Absolute value of f minus f plus the integral from a to b of the absolute value of f. Right? This is some finite value. This is some finite value. And that means we're in business. Okay, and then we're done. This was the guy we wanted to show converges. Again, we couldn't use comparison directly on him, so this is just another warning for you. When you want to use your comparison result, or any theorem, again, make sure that you're in the regime where the theorem actually works. This one, the theorem only works for non-negative functions. So we had to do a little bit of work to put this integral in terms of only non-negative functions. But we did it, and that means we could use our old theorem. And that means we can say that, indeed, this guy converges. Yeah.
You could use this to show what I said before about the magnitude.
And then you could use this approach to put bounds on the magnitude, sure.
Because those are both positive, right? On the right side. Because their determinants are positive.
Sorry, this guy is positive, and this guy is positive, yeah.
Right. So the magnitude there is less than, yeah. Okay.
The magnitude there, yeah, sure. The magnitude of this is going to be bigger than,
The magnitude of the left there.
yeah, absolutely. Because here you're subtracting off something positive, absolutely.
When you say the integral convergence, automatically you're saying it's integrable. That's all you say.
I'm saying it's integrable in terms of these improper integrals. Not in terms of our definition of Riemann integrability, where we do these Riemann sums, right? Because we know we need bounded functions on finite intervals to be able to do those. What I'm saying is that we can exclude the bad regions and take limits, and the limits will converge.
Well, what I was going to ask is, it's relevant more to the homework, but it was the multiple of two functions is integrable.
Mm-hmm.
And what I found that, like, how you're saying that they convert the sum of two functions converges. The integral of the sum of two functions converges. Can we assume anything about
The component functions?
Right.
Not necessarily, because I could split this thing up in all sorts of crazy ways, right? I could have written this as, f of x minus 1 over x plus 1 over x. and did it in a region where 1 over x is not integrable, right? I can't just split. That's why I was careful here. I said if the component integrals converge, then we can split it up this way. If the component integrals don't converge, then you don't want to be splitting things up.
I think I got that question wrong.
Okay. Okay, so we could go back to things that we did before. And we could say, what if I wanted to do this integral? Sine x over x squared dx. Well, we already did almost this integral, right? Where I stuck an absolute value on the sine x. So we know that from before, sine x over x squared converges. Okay, that means that, probably need to switch boards here. That means that the thing we started with is absolutely integrable. So this guy is absolutely integrable. And if it's absolutely integrable, we can integrate it. Right? So that's when you're faced with an improper integral and you want to ask, does it converge? That's one of the easiest tests you can try. It won't always give you an answer necessarily, but it's one of the easiest things you can try is to say, let's take the absolute value of this thing. Now all my comparison theorems work. I have simple tricks, and if that gives me a positive answer, yes, it converges, then we're in business. Absolute convergence gives us the convergence that we want. Questions on that? So what about the converse? If I have something that is known to converge, will it converge absolutely? Some tentative head shakes. So yes, the answer is no, it won't. So this is an important point also. Absolute convergence implies convergence, but the converse doesn't hold. Okay, we can't go the other way around. Okay, so here's a nice example. Let's say we're looking at the function sine x divided by x on 1 to infinity. So it's almost the same as the function we were just working with, but I've weakened the decay as we go out to infinity. All right, so what happens if we try to integrate this thing? We try to integrate this thing. This we know is the limit as c goes to infinity. Okay, I'm going to do integration by parts here. Okay, so I'm going to take an antiderivative of this guy. So minus cos x divided by x, where x goes from 1 to c. Okay, and then minus an integral from 1 to c. I'm going to get a derivative of this is minus 1 over x squared. Antiderivative of this is minus cos x, so cos x over x squared dx. Okay, and this is stuff we can work with. Okay, so if I start taking limits, okay, I get a minus cosine c over c, and then I take c to infinity. That goes away. I get a cosine of 1 over 1. And then I get a minus integral from 1 to infinity of cosine x over x squared dx. Okay, this guy, I'm not going to do exactly, but I know he converges, right? He converges for the same reason that sine x over x squared converged when we integrated it. So this converges. Actually, it converges absolutely. Okay, and that means this integral that we started with is perfectly well behaved. Okay, so f of x is integrable on this interval. And then we can ask, is f absolutely integrable? This one is a little harder to answer. Okay, the comparison tests are not so helpful here because you'd like to compare this to 1 over x. You integrate 1 over x, and you get infinity. So that tells you nothing, right? When you integrate the bigger function and it blows up, you don't know anything about the smaller function. So we're not sure on that. So here I'm going to use a little bit of a trick. It's kind of fun. It kind of also show you how these ties back to series again. So let's consider some natural number. And let's look at this guy. The integral from 1 to 2 pi n of sine x over x. Okay, what we're really wanting to do is take n to infinity to get this upper bound here, right? And what we're going to do is show that as we take n to infinity, actually we're not going to get convergence here. Okay? If we don't get convergence taking n to infinity, then we're not going to get convergence as we take an upper limit going to infinity. Okay, so I'm going to split this up. The reason I'm doing it as 2 pi n is because we know sine has this nice periodic structure. So what I really want is for things to be going from multiples of 2 pi to each other. So let's pull out the first bit that doesn't involve that. And this is what I really want. Okay, this guy's positive, right? So we integrate it, we get something positive. So this is certainly bigger than or equal to the integral from 2 pi to 2 pi n of all of this. And this is the thing that we're going to try to get estimates on. Okay, so this time I need my estimates to go greater than or equal to, right? With sine x, if we're trying to get estimates going less than or equal to, it would be natural to say sine of x is less than or equal to 1. But that doesn't help me here. So instead I'm going to use my estimates actually to handle this 1 over x term in the denominator. Okay, so let me actually split this up first. Let's do one period at a time, right? We know this sine function has this periodic behavior, and it comes back. So let's break this up into the sum from n equals 1 to n minus 1, capital N minus 1, of the integral from 2 pi little n to 2 pi little n plus 1. right? So we're going to go from 2 pi to 4 pi. Then with n equals 2, we go from 4 pi to 6 pi, and so on. We're going to cycle through all of these. And again, in each one of these, sine is kind of hard to control. All we know is that he's bigger than or equal to 0 in magnitude, which is not so helpful. But 1 over x we can put bounds on, right? This is going to be bigger than or equal to what we get when we make the denominator as large as possible, right? Make the denominator as large as possible, and we make the value of this integral as small as possible. This is just a standard comparison rule, right? So this is 2 pi n to 2 pi n plus 1, absolute value of sine x divided by 2 pi n plus 1, right? This is a finite bounded interval. This is a continuous function, and this is a continuous function. So these are just normal comparison rules. OK, and now this integral I can actually do exactly, right? So break this up into pieces. We're integrating the absolute value of the sine function over one full period, right? OK, we need to split it into two pieces and say that's really the same as doing the integral of sine x twice from 0 to pi, for example. So this is really the same as, if we pull all of this out, 2 over 2 pi n plus 1, and we just integrate this thing from 0 to pi, right? Sine x is positive from 0 to pi, and if we do it twice, then we'll get the one full period, 0 to 2 pi. Okay, and this is 2. So this is nothing but 2 over pi n plus 1. I guess if we knew anything about infinite series, we could make some conclusions at this point. At this point, we don't know anything about infinite series. Probably many of you are seeing where the conclusion is going here. So again, I'm going to use a little trick. And I'm going to say, let's multiply this by 1 and write 1 in a funny way. I'm going to write 1 as the integral from n plus 1 to n plus 2. That's equal to 1, right? Integrate this, I get x, plug in n plus 2 minus n plus 1, I get 1 back. So it's a strange way of writing 1, to be sure, but it is a way of writing 1. And the reason I'm going to do this is to try to put this back in terms of an integral. So we went from integral to sum. Now did some simplifications. Now I'm going to go sum back to integral. But it'll be an easier integral now. Okay, so again, we want this to be bigger than or equal to something. So I have these constants out in front. I still have that 1 over n plus 1 there. Okay, 1 over n plus 1 is going to be always bigger than or equal to 1 over x. Right? So I'm going to make this as big as possible by making the denominator as small as possible, the n plus 1. Again, this is a standard comparison theorem. 1 over x is continuous. It's integrable on this little interval. 1 over n plus 1, I mean, it's constant. It's all clearly integrable. So this is still a standard comparison theorem. But now this is something that we know how to integrate. True? Okay, so let me put this all together. Here we're integrating from 2 to 3, and then 3 to 4, so on. So this is 2 over pi times the integral from 2 all the way up to n plus 1 of 1 over x dx. If I put that all back together. And now this we can do exactly. 2 over pi log of n plus 1 over 2.
Such a series converges.
Right. So now we know what happens to this as n goes to infinity. Right? So what do we have? We have that the limit as n goes to infinity of 1 to 2 pi n of sine of x over x dx is bigger than or equal to whatever this does in the limit, right? Because we had that whole string of inequalities. So the limit as n goes to infinity of 2 over pi log of n plus 1 over 2. And this blows up on us. And that means this integral is also going to blow up on us. Okay, so what's our conclusion? Sine x over x is not absolutely integrable. This integral is going to diverge on us. Right? If we drop the absolute value signs, let some of the area be positive and some be negative, there's enough cancellation that we can get a finite value. But as soon as we require it all to be positive, there's no cancellation and we get blow up. So sine x over x is integrable on this interval, 1 to infinity, but not absolutely integrable. And plus a little preview of some of the techniques that we'll see again when we hit infinite series.